Ethernet is now the dominant LAN technology in the world. Ethernet is a family of LAN technologies that may be best understood in the OSI reference model. All LANs must deal with the basic issue of how individual stations or nodes are named. Ethernet specifications support different media bandwidths and other layer 1 and 2 variations. However, the basic frame and format and address scheme is the same for all varieties of Ethernet. Welcome to session 6, where we look at the fundamentals of Ethernet. In this session, at the end, you should be able to describe the basis of Ethernet technology, explain the naming rules, explain how Ethernet relates to OSI model, and describe the Ethernet framing process and frame structure. The reading list is shown, and we'll look at it. Ethernet fundamentals. Various MAC strategies have been invented to allow multiple stations to access physical media and network devices. It is important to understand how network devices gain access to the network media before you can comprehend and troubleshoot the entire network. Most of the traffic on the internet originates and ends with Ethernet connections. The success of Ethernet is due to the following factors: its simplicity and ease of maintenance, ability to incorporate new technologies, its reliability, the low cost of installation and upgrade. The introduction of the gigabit Ethernet has extended the original LAN technology to distances that make Ethernet a MAN and a WAN standard. The original idea for Ethernet was to allow two or more hosts to use the same medium with no interference between the signals. This problem of multiple user access to a shared medium was studied in the early 1970s at the University of Hawaii. A system called AlohaNet was developed to allow various stations on the Hawaiian Islands structured access to shared radio frequency band in the atmosphere. This work later formed the basis for the Ethernet access method known as CSMA-CD, that's Carrier Sense Multiple Access Collision Detection. Ethernet is considered very scalable. The bandwidth of the network could be increased many times, while the Ethernet technology remains the same. The original Ethernet standard has been amended many times to manage new media and higher transmission rates. Ethernet is not one networking technology, but a family of networking technologies. It includes legacy, fast Ethernet, and gigabit Ethernet. Ethernet speeds can be 10, 100, 1,000 or 10,000 megabits per second. When Ethernet needs to be expanded to add new medium or capability, all the IE does is to issue new supplement to the 802.3 standard. Recall the 802.3 is the standard for Ethernet. 802.11 is the standard for wireless. The new supplements are given a 1 or 2 letter designation, such as 802.3U. An abbreviated description called an identifier is also assigned to the supplements. The abbreviated description consists of the following elements: a number that indicates the number of megabits per second transmitted, the word base to indicate that baseband signaling is used, one or more letters of the alphabet indicating the type of medium used, for example, F for fiber, optical cable, and T for copper and shielded twisted pair. Ethernet relies on baseband signaling, which uses the entire bandwidth of the transmission medium. The data signal is transmitted directly over the transmission medium. Ethernet operates in two areas of the OSI model: These are the lower half of the data link layer, which is known as a MAC sublayer and the physical layer. Data that moves from one Ethernet station to another often passes through a repeater. Ethernet at layer 1 involves signals, bit streams that travel on the media, components that put signals on the media, and various topologies. Data link sublayers contribute significantly to technological compatibility and computer communications. The MAC sublayer is concerned with the physical components that will be used to communicate the information. The logical link control sublayer remains relatively independent of the physical equipment, and that will be used for the communication process. An address system is required to uniquely identify computers and interfaces to allow for local delivery of frames on the Ethernet. An Ethernet uses a MAC address that are 48 bits in length and expressed as 12 hexadecimal digits. The first 6 hexadecimal digits are administered by IEEE and identify the manufacturer or vendor of the equipment. This portion of the MAC address is known as the organizational unique identifier. The remaining 6 hexadecimal digits represent the interface serial number or another value administered by the manufacturer. At the data link layer, MAC headers and trailers are added to the upper layer data. The header and trailer contain control information intended for the data link layer in the destination system. The NIC uses the MAC address to determine if a message should be passed on to the upper layers of the OSI model. The NIC does not use CPU processing time to make this assessment. This enables better communication times on an Ethernet network. When a device sends data on an Ethernet network, it can use the destination MAC address to open a communication pathway to the other device. The source device attaches a header with the MAC address of the intended destination and sends the data through the network. When the data reaches the destination node, the NIC makes a copy and passes the frame up the OSI layers. All devices that are connected to the Ethernet LAN have MAC address interfaces. This includes workstations, printers, routers, and switches. Framing is a layer 2 encapsulation process. A frame is a layer 2 protocol data unit, or PDU. Framing provides essential information that could not be obtained from coded bit streams alone. This information would include which computers are in communication with each other, when communication between individual computers begins and when it ends, which errors occurred while the computers communicated, and which computer will communicate next. There are many different types of frames described by various standards. A single generic frame has sections called fields. Each field is composed of bytes. The names of the fields that you commonly find are as follows. There's a start frame field, address field, length type field, data field, and frame check sequence field. When computers are connected to a physical medium, there must be a way to inform other computers when they are about to transmit a frame. All frames contain some naming information, such as the name of the source node or source MAC address, and the name of the destination node or the destination MAC address. Frames are used to send upper layer data and ultimately the user application data from a source to a destination. The LLC bytes are also included with the data field in the IEEE standard frames. So regardless of the technology, all frames will begin with a sequence of bytes to signal data transmission. The LLC sublayer takes the network protocol data, which is an IP packet, and adds control information to help deliver the packet to the destination node. Layer 2 would communicate with upper layers through the LLC. The FCS field contains a number that is calculated by the source node based on the data in the frame. This number is added to the end of the frame that is sent. The SFC, recall, is a frequency, the frame check sequence. Frame check sequence. That's the FCS. There are three primary ways to calculate the FCS number. Yeah? This is mainly used for error controls. A cyclic redundancy check CRC, which performs calculations on the data, two-dimensional parity, and internet checksum. At the data link, the frame structure is nearly identical for all speeds of Ethernet from 10 megabits per second to 10,000 megabits per second. Ethernet 2 is the Ethernet frame format that is used in TCP/IP networks. When a node receives a frame, it must examine the length type field to determine which higher layer protocol is present. Some of the fields permitted or required in 802.3 Ethernet frame are as follows: the preamble, the start of frame delimiter, destination address, source address, length type, header and data, FCS, and extension. The preamble is an alternating pattern of ones and zeros used for time synchronization. An SOF delimiter will consist of one octet field that marks the end of the timing information and would contain the bits, a specific bit sequence. The destination address can be a unicast, multicast, or broadcast. The source address contains a MAC source address. The data field and padding, if required, may be of any length that does not cause a frame to exceed the maximum frame size. Then there's a maximum transmission unit for Ethernet, which is 1,500 octets, so data should not exceed that size. We now discuss the functions of an Ethernet network. We start with the concept of MAC, that's a medium access control protocol. MAC refers to protocols that determine which computer in a shared media environment or collision domain is allowed to transmit data. Examples of deterministic protocols include token ring and FDDI. Token ring is a collisionless environment since only one host can transmit at a time. If you don't have the token, you cannot transmit. Non-deterministic MAC protocols use a first-come, first-served approach. The carrier sends multiple access with collision detection is a simple system. The NIC listens for the absence of a signal on the media and begins to transmit. If two nodes transmit at the same time, a collision occurs and none of the nodes is able to then transmit any further. Since Ethernet is a shared media broadcast technology, the access method CSMA CD, that's a carrier sends multiple access, collision detection, is used to perform three functions: transmitting and receiving data frames, decoding the data frames, checking them for valid addresses before passing them to the upper layers, detecting errors. In the CSMA access method, networking devices with data to transmit would listen before a transmit, would work in a listen before transmit mode. The networking devices detect a collision if the networking devices detect a collision has occurred when the amplitude of the signal on the networking medium increases. When a collision occurs, each node that is transmitting will continue to transmit for a short time. Why? This is to ensure that all nodes detect the collision. When all nodes have detected the collision, a backoff algorithm is invoked and transmission stops. When the delay period expires, each node can attempt to access the networking media. The devices that were involved in the collision do not have transmission priority. Despite its basic simplicity, when a problem occurs in Ethernet, it is often quite difficult to isolate the source. Because of the common bus architecture of the Ethernet, also described as a distributed single point of failure, the scope of the problem usually encompasses all devices within the collision domain. Electrical signals take time to travel down the cable, and each subsequent repeater introduces a small amount of latency in forwarding the frame from one port to the next. Because of the delay and latency, it is possible for more than one station to begin transmitting at or near the same time. And this gives the collision, this is the reason, the cause of the collision. In half duplex, assuming that a collision does not occur, the sending station will transmit 64 bits of timing synchronization information. This is known as a preamble. The sending station will then transmit the following information: destination and source MAC address information, some other header information, the actual payload, the checksum as well. 10 megabits and slower versions of the Ethernet are asynchronous. This means that each receiving station will use 8 octets of timing information to synchronize the received circuit to the incoming data. Slot time is calculated assuming maximum cable lengths on the largest legal network architecture. On 10 megabits per second Ethernet, 1 bit at the MAC layer requires 100 nanoseconds to transmit. The minimum spacing between two non-colliding frames is also called the interframe spacing. This is measured from the last bit of the FCS field of the first frame to the first bit of the preamble of the second frame. The most common error conditions on Ethernet networks are collisions. Collisions result in network bandwidth loss that is equal to the initial transmission and collision jump signal. This is consumption delay and affects all network nodes, possibly causing significant reduction in network throughput. The considerable majority of collisions occur very early in the frame, often before the SFDs. Collisions that occur before SFD are usually not reported to the higher layers, as if the collision did not occur. Simply repeating 1010 pattern, the same as a preamble. When this is viewed by a protocol analyzer, this pattern appears either as a repeating hexadecimal 5 or an A sequence. Collision typically takes place when two or more Ethernet stations attempt to transmit simultaneously within the same collision domain. There are 3 types of collision. There's a local one, the remote one, and the late one. To create a local collision on a coax cable, 10 base 2 and 10 base 5, the signal travels down the cable until it encounters a signal from another station. The waveforms then overlap, cancelling some parts of the signal out and reinforcing or doubling other parts. The doubling of the signal pushes the voltage level of the signal beyond the allowed maximum. This overvoltage condition is then sensed by all of the stations on the local cable segment as a collision. So the way you detect collision is by what? Seeing an overvoltage. The characteristics of a remote collision are a frame that is less than the minimum length, has an invalid SFC checksum, but does not exhibit the local collision symptom of overvoltage. This sort of collision usually results from collisions occurring on the far side of a repeated connection. There is no possibility remaining for a normal or legal collision after the first 64 octets of data have been transmitted by sending stations. Collisions that occur after the first 64 octets are called late collisions. Knowledge of typical errors is invaluable for understanding both the operation and troubleshooting of Ethernet networks. The following are the sources of Ethernet error: collision or rant, late collision, jabber, long frame range errors, short frame collision fragment or rant, FCS alignment error, range error, ghost or jabber. While local and remote collisions are considered to be a normal part of Ethernet operation, late collisions are considered to be an error. Jabber is defined in several places in the 802.3 standard as being a transmission of at least 20,000 to 50,000 bits times in duration. That then brings us to the discussion on Ethernet.